Okay, Assalamualaikum and good afternoon. So if we recall back our notes, okay, so we learned boundary layer. So it is closely related to lift and drag force. So, and then this is the basic idea to calculate the lift and drag force here. So, and then finally we could write our lift and drag force here as this equation. Okay, so in boundary layer, we try to focus on drag force here. So that's why in our topics, we are focusing on flat plate. Okay, because I think in our last notes here, you understand that if we are using another shape, for example, aerofoil or sphere or cylinder, or we have a vertical flat plate like this, we found that the drag force, okay, due to pressure, so mean the force or the resistance due to pressure will occur. So here, when we have a very thin surface here, so the resistance is only a come from the skin friction. So what is skin friction here? So the skin friction here is actually the value of shear stress, because according to this diagram, we know that the tau A here is actually the resistance that occur on the surface. Okay. So if we see this equation, we will find that this term is actually pressure that comes out from the, this is the force which is come from the pressure. So when we use a flat plate like this one, so we assume that the pressure here is very small, so we could neglect the value of this one. Then we only focus on shear stress that occur on this surface. Okay, so and then so to calculate the pressure, to calculate the force here, so we found that according to the equation, we need to calculate the value of tau. Okay, then now from the idea of Von Karman, okay, by the idea of Von Karman equation, okay, we could simply estimate the value of tau. Okay, so saya harap awak dapat, awak mula nampak di sini bahawa kita semakin mendekati untuk mengira nilai drag force kerana kita akan belajar tentang idea Von Karman di sini yang akan mengeluarkan formula untuk mengira nilai tau. Okay, so here we will show you the derivation about the Von Karman equation, and the main purpose here is actually to estimate the value of shear stress. Then when you get the shear stress, you could calculate lift force and drag force actually. Okay, Von Karman, it is introduced by Von Karman, a scientist between 1881 to 1963. And it used the idea of conservation of momentum. So the idea is very simple. The idea is, for example, we have a set of molecule moving with a free stream velocity like this. So, and then because there are no resistance, so we have no resistance at the bottom here. So all the velocity here will move with speed of capital U. So I just write this one like this. Okay, just to show it is a capital U or a free stream velocity. So and then when this molecule flowing over the plate like this, so we know that the velocity at the bottom here, okay, it will stop because we have one phenomenon called no slip condition. So dia akan melekat kuat pada permukaan solid. Oleh itu, kita kata had laju akan menjadi kosong. Walau bagaimanapun, pada molekul yang lain akan bergerak dengan had laju yang pada mulanya kecil dan semakin membesar sehinggalah. So at the top here, so we assume that the velocity will back to free stream velocity, capital U. Okay. So now if we see this diagram, we could say that there is an empty area here. So this area is actually occur. Okay, this area is actually occur because there is a momentum loss. So and then what we need to do, we need to balance we need to balance the momentum at inlet here with the momentum at outlet, because the basic idea of von Karman equation is to conserve the momentum value. So and then momentum can be calculated. Okay, the equation for momentum is mass time volume. So and then we could write, okay, I'm sorry, this is, okay, so mass, so we know from the equation for density, rho is equal mass over volume. So and then mass can be written as rho time volume. So that's why I write here mass is equal rho time volume. And the value of V here is the velocity of the molecule. Okay, then we need to create a diagram. So let's say this is the diagram. So we assume that the top molecule here, it is moving with a capital U, which is the free stream velocity. And then we are now calculating the momentum inside this area. Okay, so we start, because the shape here is a curved shape, so we cannot calculate it by using the idea of triangular area. So what we do is we assume that we have a very small area of this one. Okay, let's say we have a rectangular, a very thin rectangular. Kita anggap kita ada satu area berbentuk segi empat. Okay, bujur gini. Okay, and then we could assume that the thickness of this rectangular is dy, because this is the axis of y, and the length here is capital U minus U. Why? Because at this one, okay, so the value is free stream velocity, capital U, and the molecule here is moving with the velocity of small u, which is the local velocity. So this is the local velocity. Okay, and this is the free stream velocity. Okay. So then we develop the momentum for this small area. Okay, so mass kawasan yang berlorik. So kita tahu mass it is equal to rho times volume. So volume, rho is rho, and volume here is actually the volume of this rectangular area. So if we have a rectangular like this one, so the volume can be calculated by multiple this length, which is capital U minus U, and then the thickness of this one, so which is the dy, and also the width of this rectangular, so which is b. So that's why we have the mass for the shaded area is rho u, capital U minus u, b, and dy. Okay, so this is the mass for the shaded area only. Okay, here. So, and then we could say that the momentum losses, the momentum loss for the shaded area, so with a small d here, can be calculated by using the idea of m times v. So, which is m is mass and v is velocity. So, mass is already calculated previously. So, we get it is equal to rho capital U minus U b dy. And then we need to multiply with velocity. So please remember here, the velocity is actually the velocity of the molecule. So the velocity here must be written as small u, the local velocity. Okay, please remember this idea, because sometimes student takes u minus u as the velocity. So and then, so what we have here, okay, what we have here is actually the deficit momentum for the shaded only shaded area only. So how to calculate all the momentum loss of this area? So we need to do the integration. So we integrate that one. So to calculate the total momentum loss or momentum deficit, so we assume that the small d is now become a capital D. So it is equal to rho b integration of u minus u and dy. So here is actually you could derive from this one. So we have the integration of d here. So and then we have the integration of rho u capital U b dy and u. Okay, because we want to integrate with the idea of y, and means that the rho here and also the b here is the constant. So we could put it outside the integral symbol. So now we have u minus u with another u here and dy. So that's why we get these terms. So and then if we a little bit arrange this equation, what we do is we multiply with u square over u square. So that's why we have u square here. So another one, you could see we have u times u here and u times u here. So the idea is, okay, I hope you could do this at home. So we multiply this one with u square over capital U square. So the u square here will goes here, and then the u square is actually will become at this term. So and then, so after we multiply with u square over u square, so I hope you understand when we multiply with u square over u square, so the value is remain as 1. So means we just multiply with 1 here. Okay, so means that it's not changing the total value. So if we, after we multiply with u square over u square, for this term, we could rearrange it so it can be write as u over u 1 minus u over u. So this equation is familiar with us because previously we derived this equation, which is it is equal to theta. So means that now we could say that the deficit momentum d is equal to rho b u square and theta. So now we assume this equation as equation number 1. So and then to simplify our calculation later on, so we integrate with we differentiate with dx. So we have dd over dx here. So it is equal to rho bu square d theta dx. So as, and then we label it as equation number 2. Okay, so then we assume that why momentum deficit occur. So it is occur because there is friction. So I think you could imagine that. We already learned this in fluid mechanics 1. Why we have a velocity distribution here? Because there is a friction here. There is a resistance on this surface. That's why the velocity will become 0. So, and then friction here, if we see back the idea of Newton law, Newton viscosity of law of viscosity. So we could say that if we have a fixed plate here, and then we have an oil here or a liquid here, so and then we have another plate on the top. So you need certain force, okay, to pull this plate. So why? Because there is a resistance occur by this fluid. So why this resistance occur? Because it has shear stress. Okay, shear stress. So, but we don't always mention as shear stress. We will call as viscosity, because dynamic viscosity is actually shear stress is equal to mu du dy. Okay, we call it as the viscosity effect of this liquid will give us resistance. So we need certain amount of force to pull this plate. Okay, so means that because the deficit momentum here is caused by friction, so means that we could say that the momentum deficit is actually can be equalized with the force here. So that's why we could equalize dd here. So it is equal to tau dA. So means that the deficit momentum that occur at this plate is actually, it is equivalent to the force that used to pull that plate. So this force can be calculated by using the idea of tau and dA. So this idea is learned in fluid mechanics 1. Okay, so we equalize dd here, mean momentum, deficit momentum for a small area. So it is equal to tau dA, and then we could replace the value of dA here with b dx. Why b dx? Because if we enlarge this area, so for example we have a plate here, so this is a very small area. So because to calculate the area, so this is the area. So if we draw it in 3D, so to calculate the force according to the shear stress, we need to calculate the area. So the area must be this area. So how to calculate the area of this one? So we need to know what is the value of x-axis here. So and then we need to multiply with the width. Okay, so the width is b, and because it is only a small area on x-axis, so we call it as dx. So that's why we replace the value of dA here with b and dx. So and then we bring the dx to the left hand side, so we'll have d over dx. It is equal to tau b. So that's why in this calculation we purposely, okay, differentiate this term to dd over dx, because it is easy for us to equalize these two equations. So mean finally we need to equalize equation 2 and equation 3. Okay, so here you already understood that the momentum loss is actually caused by the friction. So and then we could write dd over dx, it is equal to tau b. Then we equalize equation 2 and equation 3. So we have d dx equal to rho bu square d theta dx, and it is equal to tau b. And here we could cancel the value of b here, means that if we don't know the value of the width of that plate, we still can calculate the value of drag force later on. So and then this equation can be rearranged, because as I said, we need to know, or we need to estimate the value of shear stress. So now we have a shear stress here, so means that shear stress later on can be calculated by using this equation. So we call this is a Von Karman equation. So we have tau equal rho u square d theta dx. So I hope you could remember this equation. At the same time, maybe okay, we ask you how to derive or how to prove the Von Karman equation. So here, okay, you need to calculate the value of theta. That's why in our first introduction, we ask you the equation of delta, delta star, and also the theta. And also we show you the calculation of delta star over delta, and then the theta over delta. Because in this part, we need to calculate the value of theta first before we could proceed with this calculation. Then, okay. So and then because we assume that it is equal to friction, so means that theta also, I'm sorry, tau also can be calculated by using the idea of Newton's law of viscosity. So what is Newton's law of viscosity? As I said, tau is equal to mu du dy. Okay, but in this topic, in boundary layer, we must have a condition. So what is that condition? Is that condition is du dy at y equal to 0. So y equal to 0, because if we have a flat plate like this one, so we know that the velocity distribution occur like this one, and then the shear stress, the maximum shear stress occur at this location, because the shear stress is very high. That's why the velocity is equal to 0, and we call this is as no slip condition. So means this location is occur at, so this is y-axis, so it's occur at y equal to 0. So that's why I hope you could understand that shear stress using the Newton's law of viscosity, so it can be calculated. So it can be calculated by using this idea. Tau is equal to mu du dy at y equal to 0. So now means you, I already introduced you two equation. One is Von Karman, tau is equal rho u square d theta dx, and another one is tau du dy. You already learned this equation in fluid mechanics 1. But for this topic, for boundary layer, we will use condition of y equal to 0.